pleasure to be here. Great. So today I wanted to talk about some recent progress on our understanding of gas in planet-forming disks. Just to bring everyone into the same picture, is this working?
Can you click your mouse on the screen one more time? Yes, go back.
Yeah, it's working now. Okay, great. So just bring everybody into the same picture. One of the fundamental questions in astronomy is trying to understand how planets form and how we can build habitable worlds. So one important aspect for us to understand how planets form is to look at their formation place. So those forming planetary systems, the natural byproduct of star formation. Inside a molecular cloud, some particles may become gravitationally unstable and start to collapse. And because of the angular momentum need to be conserved, you naturally will have an accretion disk. Most of the materials will channel through the accretion disk to the growing young star. So this forming flattened disk, it's the place the future planetary system is going to be built up. And the initial phase, when there's still a lot of enveloped materials going to the accretion disk, this is the forming stage, but this won't last very long. On the order of 1 million years, the envelope is going to be gone, and you ended up with an accretion disk around a pre-main sequence stars. So this stage, we generally call it protoplanetary disk. And for this talk, just for simplicity, I generally refer at this stage forming disk and the protoplanetary disk stage as protoplanetary disk. So this stage can last a few million years. It's pretty short compared to many astronomical timescales, but it's really at this stage we set up many fundamental properties of planetary system. It's at this stage micron size interstellar particles really need to grow to centimeter size pebbles to kilometer size planetesimals and eventually to planetary cores. In particular, if we want to have any gas giants, it has to accrete its gaseous envelope during this protoplanetary disk stage. So it's very important for us to understand the evolution of those planet-forming disks, how their physical and chemical properties evolve during this stage. In particular, one of the most fundamental property of protoplanetary disk is their mass. So their mass is like stars. Most of the mass is in hydrogen and helium. And due to their cold temperature, most of the mass is in molecular hydrogen. And the amount of mass is really great importance for future planetary system, because how the dust particles they interact with each other also relies on how much gas around it, so it regulates the dust dynamics. And also after the planetary core formed, how massive the gaseous envelope can be accreted also depends on the gas reservoir at that stage. So whether we form gas giants, ice giants, or super Earth or mini Neptune also depends on how much gas mass at that time. And also after the planet form, it may migrate across the disk. Whether it migrates inwards or migrate outwards, how fast it migrates also depends on how much mass available at that stage. So the gas disk mass is a fundamental property and plays an important role in almost every step of planet formation. But unfortunately, we don't fully understand how gas evolve in protoplanetary disk. We know the key is to understand how angular momentum is transported or removal from those disks. But what mechanism drive this angular momentum removal or transport, we don't fully understand. So there have been two leading theories about the angular momentum transporting disk. So one is the angular momentum is transported due to the turbulent viscosity in the disk. So in this case, most of the material lose their angular momentum and they move inwards. And small amount of material, they carries angular momentum, they gain angular momentum and moves outward. So the disk would spread over time. Another idea is related to the magneto-hydrodynamic disk wave. So in these cases, materials get all accelerated when they move along the magnetic field line. And then when they get enough momentum, they would leave the disk. So in this way, they carry angular momentum away, and the disk materials, the rest of the disk materials lose angular momentum and they move inwards towards the central star. So those are just the two leading theories. We don't know either one, which one would dominate or either, whether each one, any of them are really correct. So there have been a lot of effort trying to understand the evolution mechanism of disk mass. So there has been two approaches. One is the individual view. So we're trying to look at signatures of what the mechanism predicts. For example, if the disk involved is driving by turbulent viscosity, so we expect that we can measure the turbulence level in the disk and to see whether this matches with our expectation. But it turns out it's very hard to measure the turbulence level. So various efforts have been carried out, but most of those results tend to be negative results or upper limits. Only a couple of disks we have measurement. So it's very hard. Another way, people also pushing really hard to look at disk wind tracers, but this is also elusive, so there is no conclusive conclusion yet. So besides those individual view approach, we can also try population view approach. So this is like you study HR diagrams, you're trying to look at stellar evolution as a population, how as a population, the disk mass evolve over time, the disk size evolve over time, accretion rate to the central star, and how those property evolution depends on the stellar mass. So in this way, you would need a population, right? So you wanted to have a large sample in order to study the evolution. But so far, those evolution has been mostly limited to study of dust mass rather than the dominant gas mass, which is the main mass component. But at least we know those protoplanets, they evolve over time, which can be looked at two different lines. So one is we know the fraction of young stars, they have protoplanet disk. The disk fraction decrease over time. So we can look at those as infrared access. So this is early example. You say the young star, it's photosphere, but you have extra infrared flux. That's an indication of those young stars. They have a dusty materials around it. So the disk fraction based on infrared access, it has been well known, it decreases over the age of young stars. So that's the indication of evolution of protoplanets. And this has been known for 25 years and more. Over the past 10 years, thanks to the sensitivity of ALMA, now we can do sub-millimeter continual observation of those protoplanet disks to look at their dust mass, which measured by the millimeter continual flux. So again, you say in those disks, you say for a few million year disk, 1 to 3 million years, they have a median dust mass on the order of 1 Earth mass. But when you move into 5 million year protoplanet disk regions, you can see a significant decrease of the amount of dust mass over time. So all of those pointed out, we know protoplanetary disks, they evolve on the scale of a few million years. But still, we don't know how the dominant amount of materials, the gas materials, they evolve over time. So if we can measure the gas disk properties, we measure their mass, we measure their size, And current theory prediction can be tested. So this is two examples of how viscous disk evolve over time compared to wind driving case evolve over time. And we can choose disk at different ages. So can sample different star forming regions. They have different ages, and we can test those predictions, how well the observations match with our theoretical predictions. So that was the motivation of the ALMA program H-Pro. So the ALMA survey of gas evolution in protoplanetary disk. So we call it H-Pro. Yes,
Brian has a question online.
oh, can you read it?
Oh,
Oh, no, I can you hear me?
Yes,
Yeah. So on the earlier plots, when you showed the observations as a function of the age, I was just wondering how the age is measured. Is that from the stellar evolution?
yeah, so those are mostly from the evolutionary tracks. So you
Yeah.
plot the effective temperature luminosity and compare with the evolution of pre-main sequence stars.
Yep. Got it. Thanks.
The isochrome ages.
Do you believe those isochrome images?
That's a great question. So I don't believe the absolute age, but the relative age is more reliable. So we know those different star forming regions, some probably older than the others. Yeah. Yeah, so our goal is to try to provide the first systematic population study of gas disk mass and size throughout the lifetime of protoplanetary disk. So this was approved 4 years ago. So it was about 100 ALMA time to do this. So we are wrapping up the program, and hopefully you will see the papers in 1 to 2 months. And so what I'm going to present today is really the effort of the whole team, particularly the junior people's postdocs, graduate students. They really did the heavy lifting work here. So our sample selections, we selected 30 disks, trying to cover the typical lifetime scale of protoplanetary disk. So those disks are lifted to be 0.1 to 6 million years, and primarily selected from 3 star forming regions to sample different ages. So because individual disk ages are hard, so we try to narrow down to different star forming regions to represent different ages. So for UCAS, we selected class 1 sources, supposed to sample less than 1 million year disk, and lupus 1 to 3 million year, and upper school 2 to 6 million year. And you can see the individual stellar property compared to evolutionary tracks. So you can also see for the sample for the youngest population, they have brighter millimeter flags compared to the middle age and old ages. So there's generally a decrease of millimeter flags over time. So because the protoplanetary disk evolution is expected to be stellar mass dependent, so we try to narrow down the sample to a limited stellar mass range. So we focus on stellar spectral type M3 to K6, so roughly 0.3 to 0.8 solar mass stars. So this choose is because higher stellar masses, there are much smaller number of disks, and for lower stellar mass sources, they are much fainter. So this is like a compromise, trying to have enough sample and bright enough. So we try to limit our sample to single system or at least wide separation binaries, because the close binaries, they may have strong impact due to the tidal interaction with the companions. So we also try to choose the regions, the disks, at least on the HR diagram, close to the median estimated ages for each region. Okay. So one of the fundamental challenges for this program is to how we measure the gas disk mass. That's the limiting factor. Traditionally, for molecular clouds, people either use dust continuous emission or extinction and convert it to a gas to dust ratio 100 to estimate the gas mass. Or they measure the CO gas mass and convert it with abundance of 10⁻⁴. But for protoplanetary disk, both some assumptions could be problematic. So we can use millimeter continuum emission, but that's conversion to dust mass related to the opacity. So we measure, because the dust need to grow larger and larger, that may change over time. And also the gas to dust ratio in protoplanetary disk may also evolve over time. So using dust as a mass tracer is intrinsically questionable. So another approach is using the CO gas. Because the CO is the most readily detectable gas in protoplanetary disk, and it has relatively well understand the chemistry, at least for the molecular clouds. So, but the question is the assumption of CO to H2 abundance ratio, is that still 10⁻⁴ in protoplanetary disk? So from samples people have studied before, it seems there is a wide range of CO to H2 abundance, particularly for the class 2 disks beyond 1 million. So there are 2 orders of magnitude spread on the possible CO abundance. There is high uncertainty. When you have the CO gas mass, you cannot accurately enough convert it to the H2 gas mass. So what we did is we added another chemical tracer, which is sensitive to the CO to H2 abundance ratio. So this particular molecule is N2H+. We choose it because N2H+ can be easily destroyed by gas phase CO, so to form HCl+. So it only becomes abundant in the CO poor environment. Also, the formation of N2H+ is a competition of N2 and CO for the available H3+. So both the formation and destruction wave suggest N2H+ can only be abundant in the CO poor gas. So when CO to H2 ratio is low. So you can use this as an additional calibrator to measure the total gas mass. So you can measure the CO to N2H+ to CO ratio, and using that to narrow down the possible CO to H2 ratio in the gas. Okay, so you may wonder, this is great theoretical prediction. How do you know whether this is correct or not? So luckily, there are 3 protoplanetary disks. They have some benchmark test about their gas disk mass. So those were measured by Herschel Space Telescope working in far infrared using HD 120 line. HD is deuterium version of H2, so we know the conversion factor of HD to H2 pretty well. So for the 3 disks, we know their H2 gas disk mass. So this is a benchmark test. So we have the C18O line flags of those disks. So you can use this to measure the CO gas mass. And if you don't know the CO to H2 ratio, you have to put on the whole range possible CO to H2 ratio. So that's 2 orders of magnitude range. So all the color dots are the possible gas mass using CO alone. But once you add the N2H+, you have the N2H+ to C18O flux ratio. You know the CO to H2 abundance, and you can dramatically shrink the possible range. So the orange box is once you add the N2H+ information, so what's the predicted the gas disk mass. And you can compare this with the gray box, which is the HD constraint on the possible gas disk mass. So generally are consistent with each other within reasonable accuracy. So because currently we don't have a far infrared space telescope to do more HD observations, so we think this is a good way for us to measure gas disk mass in a large population of disks, because we could get the CO flux and enriched plus line flux with ALMA for a large number of disks. So that was the foundation for H-Pro, particularly for the observations. So we have continue, and we have 3 CO isotope log lines, 12 CO, 13 CO, C18O, so to probe different optical depths. The 12 CO is mostly used to measure the gas extent of the disk, how large those disks are. And the line flux for the CO isotope logs and enriched plus are combined to use the gas disk mass. From those spectral setups, we also get some molecular lines for free. So those are example lines covered in the same spectral range. So, go ahead. Yes.
In these disks, is the surface density profile such that most of the mass is at the outer edge of the disk? Or is it deep inside?
It's expect to be most of the mass are beyond the 20 AU. So yeah, so typically we assume this gas surface density is a power law either -1/2 or -1. So we don't have enough spatial resolution to map out the exact distribution, but the current data suggests those are reasonable assumptions. Yeah, and in those assumptions, most of the mass should be in the outer part. Yeah.
So the N2H plus seems to be centrally peaked, but so is the CO. So where is the, I thought the two would avoid each other more than what we're seeing here.
Yeah, so one thing is you say this is the CO spatial resolution. It's much higher than the N2H plus. So the N2H plus we're taking a lower spatial resolution. So we would really expect that you have some kind of small cavity. But so the cavity expect to be smaller than the beam size, so it's harder to tell it exactly. Yeah, but this N2H plus, because we focus on the bulk properties, we just use the line flux. But there are a few larger disks that they have N2H plus. Or spatially resolved observation, you can see the cavity at the center.
Can you see a difference in the line profile, even if you're not spatially resolving it?
Not enough because yeah, so this CO snow line is already like 20 AU, so in the outer part, the difference is not that big enough. Yeah, so those are the 30 disks. They're showing you the 1.3 millimeter continuum. So our typical resolution is like 0.3 arcseconds. So you can see many of the disks are pretty small. We considering our sample is more like a typical disk between this stellar mass range. So many of the disk images you may have seen like HL tau, so those are really big disks. And this is the CO image, 12 CO 2-to-1 line images for all of the sample. So of Euclid samples, they are more embedded compared to the class 2 disks. So you see those irregular features, and those are because they have envelope contaminations. So from the H-Pro results, we have 12 papers and hopefully coming out soon, including an overview paper explaining the design of the program and highlights the most important results. And we have 3 papers focused on each of the star forming regions to explain the observations and present all the images and statistics. And we have 3 papers to measure the fundamental disk properties we care about, including how we measure the gas mass, how we measure the gas disk size, and how we measure dust substructures in the sample. So we have also 3 theoretical papers on trying to put our results into the theoretical context. So including 1 paper comparing the dust involution models with H-Pro. So we sample the continuous class ages. And we have a paper doing population synthesized analysis comparing our gas mass, gas size involution with viscosity involution and MHD disk wind involution. And finally, we have a paper to estimate the impact of external photoevaporation on our sample. So in addition to those main sites we originally targeted on, there are two actual surprise papers. One is one of our disks. We find a big cavity inside this one. So it has some indication of potentially a circumplanetary disk. And we also have a source which shows extreme variability in the millimeter continuous flux. So it changed by order of magnitude within a couple of hours. So yeah, so those are additional papers. So those are our first group of results, and all the papers, and majority of papers have been accepted, and just two more papers at the revision. So I wanted to highlight a couple of the most important results. One is for the gas disk mass. So how we measure this? You have known, so our fundamental method is to use the N2H plus to see CO isotope log ratios to calibrate the CO2H2 abundance. And then we take the CO gas mass from the rear is the CO isotope logs we detected. So our method is we compare those fluxes with a large grade of thermo-chemical models, which started with some initial conditions with different CO gas abundance, and to predict the line flux of those lines. So this is a pretty extensive investment on the computational hours. So we have like 3,000 models and took almost 1 whole year to generate. So we take the measured flux and use our extensive grid as to interpolate, to estimate the posterior distribution of the gas disk mass and the CO abundance. So you can see the probability distribution, how will we constrain those parameters based on the uncertainty of the line fluxes. Okay, so those are the 30 disks we measured, plotting in the dust mass versus the gas disk mass, with different colors for different star forming regions. So the most important you can see on the median value, which is here, the Ophiuchus region, which is the youngest region, you see this is on the median significantly 1 order of magnitude higher gas mass than the 2 older regions. But for lupus and upper skull, there is a small difference, but not as significant as the younger region, the difference. So it was a surprise, and the lupus and upper skulls, they have similar gas disk mass. This is when we look at the dust mass evolution. Also we go one. Yeah, so this is the median dust disk mass. You can see the steady decrease across the 3 regions. But when you look at the gas disk mass, it's like this. So it decreases quickly first and then flattens out. So we went back to check our data to see, is this how we interpolate the data? But when you really look at just the line flux, so you see the millimeter, the cumulative distribution of millimeter flux for the 2 samples, the lupus versus upper skull. So this is the percentage of the disk with fluxes lower than this. So you can see a significant difference in the dust mass distribution, millimeter flux distribution. So when you look at the line flux, the 2 samples looks pretty similar to each other. So this is suggesting no matter what models you use to interpolate the data, you will find the gas mass of the 2 populations, they are pretty similar. Yeah, so this is the distribution of the 2. The continuous flux, you can see the offset, but when you look at the Y range it covers, those 2 range covers pretty similar flux range. Okay, so that's what we find. It seems to be the dust and the gas, they involve a different time scale. And this lead to an interesting swing on the gas to dust mass ratio in those disks. So you started with about 100, what you expect for interstellar medium. And then in the middle age, so the gas to dust ratio decreases. But later for the older sample, the gas to dust ratio actually increased back to 100 level. So this was unexpected because traditional idea is you more or less expect the gas to dust mass ratio decreasing over time. Okay, so another main properties we measure is the gas disk size. For the embedded disk, as you see, they are pretty contaminated. So we are exploring using the velocity gradient to identify where the disk end. So this paper is still in preparation. For the class 2 disks, they are mostly clean, and we measure the cumulative line fluxes reaches 90% of the flux as the disk size. Okay. So this is a comparison of the gas and the two dust disk size. We can say for the two lupus and upper spore regions. So the dust disks on the order of nearly 30 AU, and the gas disk on the order of 70 to 100 AU. But gas disk is not that much larger than the dust disk. So for many of the disks, we find their gas disk are actually small. So with a medium size on the order of 70 to 100 AU. So this is much smaller compared to many of the well-studied large disks. They are usually a few hundred AU, 1,000 AU. So this is showing really for the typical protoplanetary disk around 0.3 to 0.8 solar mass stars. Their gas disk size is not that large, on the order of 100 EU. Okay, so once we have those properties, we can start to try to put them into theoretical context, trying to understand the disk evolution. So this is a composite figure to look at the properties we constrain from the program. I'm saying the dust disk mass, so the medium value, the gas disk mass. You see, each region has a wide spread, but the medium value seems to have some pattern. And the dust disk size, you can see, interestingly, it does not change much over time. So that's suggesting there are some mechanism blocking the dust drifting inwards. And this is the gas disk size. We also measure the gas to dust size ratio. From the mass measurement, we also get the byproduct of the CO abundance. So those two regions are actually pretty similar. When you look at the absolute value, they are both significantly depleted. So 10 to minus 5 compared to the typical ISM value, 10 to minus 4. So it's really important to correct the CO abundance. Yeah.
In the vertical dispersion dominated by the sample dispersion or measurement uncertainty?
Not really. When you look at, so people have done shallower study of dust with the whole population of each star forming regions, like 100 to a few hundred disks. You still see a wide spread of properties within the similar stellar mass range. So there seems to be intrinsically a large spread on the disk property. Yeah. Yeah, so we also measure the two wavelengths because we have two spectra set up, so we can measure how the continuous flux changes with wavelengths. That's also usually used to constrain the dust particle sizes. So those things, you see a small increase in upper spore ones.
It's in the same band or is that different bands?
Different bands, band 7 and 6. Yeah, but the leverage is not that huge. So N2H plus setup is like 100, so 280 gigahertz basis to 30 gigahertz. Yeah. Because we have two spectra setup, we can also leverage on it. Yeah, so the dust evolution, so we compared what we say the dust evolution with theoretical models. So this was carried out by postdoc in our team, so Nicholas and Matthias. So they were postdocs at the MPIA and MPIE now. So what they did is they run an extensive grade of dust evolution models, considering dust particles, they collide with each other and they grow to larger sizes. Under a viscosity involving disk, and run this simulation for 10 million years. They try to start with different stellar and disk properties, different stellar mass, different initial dust mass. And they also simulated with different number and amplitude of dust caps. So this you can think about, you can put different planetary mass at different locations. You can put a Jupiter at 10 AU, you can put a Neptune at 30 AU. So they would open gap in the disk and block the flow of dust particles to migrate to the inner disk region. So once they have the simulations, they take the dust opacity and do simulations of ALMA observations. So this is their model. You can say after the simulated ALMA observation, this is what you would really see with ALMA. And they compare their models with our observations. So this is a pretty busy plot. So focus on the bottom one first. So different stellar masses and how bright the disk would look like. So this is spread just for different initial conditions. Basically, you can see the evolution pattern. So for this one is if there's nothing in the disk to stop the gas inward flow. So how the observed millimeter flux will change over time. You can say generally, this is showing this observed millimeter flux will decrease over time. But if you have something, we call it pressure trap, maybe a Neptune-sized planet to block the inward flow, the decrease will be slower. If you have even stronger pressure trap like Jupiter planet to stop the flow, so the decrease will be even slower. And compare with our data points, so you can say the medium pressure trap level and the stronger pressure trap level have a better match with the data compared to the no pressure trap one. Yes.
So if the disk is massive, you might think it would actually induce migration of the planet. So is that something that you can model?
Yeah, you can model, but in their cases, they just have 3 locations of the pressure type. So 10 AU, 30 AU, 70 AU. Yeah.
So they don't consider that.
They don't scale things. The scale is just if the disk size they started is smaller than the pressure trap location, they just ignore the outer pressure trap. So the pressure trap has to be located inside the disk. So in that case, larger disk, they may have outer larger pressure trap at the outer regions.
Okay, but their planet doesn't migrate, it stays in one.
Yes, stays at
Okay.
the same place.
But your data, the observations didn't show any obvious dust traps at large radii.
No, we don't see clear dust trap at the outer. Yeah, because our medium disk size in the dust is like 30 AU.
Right.
Yeah. Yeah, so we also compared it with the model spectral index, which is an indicator of how big the dust grain has grown. So you can see if no pressure type, so you see this, the pressure type look, the spectral index distribution at different ages. Again, you see the model really predicted their outer disk would only have small dust grains corresponding to higher alpha. While in our observations, we see significant, actually the majority of them have lower alpha compared to the models. So it's really strongly against the no pressure type case. And we find that generally the weak traps, considering everything, are better reproduce our observations. So the dust evolution is our hypothesis is there are some the weak pressure type must be common in those protoplanetary disks in order to reproduce those millimeter flux and spectral index. Okay, so finally we reaches the populations in this model. This is also one of the fundamental goal we wanted to test. So we wanted to test turbulent viscous disk versus MHD disk wind models. Which one can better reproduce our observations? So we have several observational constraints. We have the disk fraction. We know the number of young stars with disk decrease over ages. So we try to reproduce those. We also know the accretion rate, the mass accretion onto the central star, which can be measured by UV or accretion tracers at alpha. So measure how much flux goes to the central star on average. So this is from other observations, not from H-Pro directly, but for the same star forming regions, we have constraints. And we know the gas disk size in our measurement, so the median value and the individual value. And we also know the gas mass across the three regions. And those are the observables we're trying to reproduce with the population synthesized models and see which one does a better job. So the idea is you have a population. Initially, there is a spread of disk properties, like the initial disk mass, and also other analytical parameters like accretion time scale to let it evolve under different mechanisms. So in this way, we try to match the observables as close as possible. So we find out the MH disk wind, which does a good job in general to reproduce the bulk properties and the disk mass, accretion rate, and the gas disk size. So this is already matching the disk fraction. Okay. And for the viscous evolution model, so we could reproduce the accretion rate and the CO gas disk size evolution in some parameter space, but all of our models are just having some difficulty to reproduce the gas mass evolution. So the current test is our results pointed out MHD disk wind model better reproduce the evolution pattern we see in those observables. So yeah, we are hoping to get more data to the even older disks. Yeah, so if you're on the ALMA panel, this cycle help. Yeah, so this is the probability distribution for different population synthesis models. So the red dots are our data. So the disk mass, gas disk mass, this is the accretion rate. And the darker the color means higher probability. So within 90% of probabilities, we can reproduce all of our data for the MHD disk wind model. Compared to the turbulence models, you can see it's harder to reproduce some of the disks here. Okay, so finally, I want to talk about two follow-up programs for the sample for H-Pro. So we have a JWST Cycle 2 program to look at the same sample. So JWST can observe infrared spectral line from protoplanetary disk. So you can see example spectra here. You see waters. Those are mostly waters, but you can also see organics in the spectral range. So lots of information about the chemical composition from the hotter part of the disk. So generally 1 AU or inside. So we get 10 to look at the same sample, 30 disks, to look at how the inner disk chemistry, chemical composition evolve over the protoplanetary disk evolution stage, and how this may relate to the outer disk property evolution. So we wanted to understand if any dust particles they grow and drift to the inner disk may change the inner disk chemistry composition. So we have gotten all of the data. So analysis is underway. So example to show you the 3 regions. So in the off-focus region, we see those ice absorption features probably from the envelope material. But on top of it, you see those molecular emission lines. So here are the waters and organics. You see the broad feature here. This is the middle age one. You see a lot of water lines and other organics. But when you really go to the oldest sample here, you see the much fainter and less water compared to the younger ones. And when you try to really to put at the individual water line luminosity, so there's two water lines sampling different upper energy level. So basically think about the hot water and cold water. You can really see the three regions represented by different colors. There is some significant trend from the brightest water to middle water and cold less water. So there's some evolution involved over with the ages. And also when you look at the oldest disk, the upper disk samples, even their lines are much fainter. Interestingly, you do see more organics. So you see those long carbon chain molecules and more complex ones, which are rare in the younger samples. Those are preliminary, but we think there are some evolutions and we are working on it. And finally, also from this sample, we noticed some interesting things. So this is our embedded disk sample, so the ones less than 1 million years. So they have abundant water, bright waters, but they are really faint on the CO2 features, which is one here. So compared to many of the class 2 disks, you see the CO2 low vibrational features here. So it's interesting. This is also suggesting those younger disks in the inner disk, they may be CO2 poor. And this is consistent with the current pebble drift models. Current pebble drift models predict most of the pebbles and the pebble mass, they drift inwards. If no pressure trap, the most of the flux will be high in the first 1 million years and decrease over time. So in this naive picture, you will expect more water in earlier times, less water at later times. And also when you look at how the CO2 to water pollen density at 1 AU would change over time based on how much materials the pebbles drift inwards. You will also see the younger ones, they may have lower CO2H2 ratio in this 0.1 to 1 million year stage. And the C over O ratios increase over time after that. So you expect to be more carbon rich for the later days. So this is of course very preliminary, but we do see some interesting trends here. So we also recently get a new JWST program to look at the youngest generation. So to look at particularly this phase to have a larger sample. So we get a time to do 40 disks in total, plus 10 we already have. So to look at the class 1 population in the Ophiuchus region, particularly look at the 0.1 to 1 million year stage to see if they are all water rich or how they depends on the disk property. So those are the 40 disks, and most of them we have high resolution ALMA images from our collaborator. So they have 5 AU-ish dust studies, so we know the substructures inside those disks, and we can try to understand how the substructure in the earlier stage may impact the water budget to the terrestrial planet formation. Okay, so that's a lot. For the next few years, I hope we'll also have some exciting results to present. So in the end is, so take-home messages, AgePro is the first systematic ALMA program to study gas evolution. So we measure gas mass and size in 30 disks. Interestingly, we find the gas and dust, they evolve at different time scales. And current results favors HD disk range evolution. Yeah, but still a limited sample. And we hope there will be more gas studies in a large population in the future. Thanks.
Can you say a little bit more about the millimeter variability?
Yeah.
Yes.
Great.
Great.
It's
Um,
huge.
backup slides for this. So usually ALMA, those observations are taken in like a 1 or 2 hour observational blocks. We observe the multiple sources together as a cluster. So you can see this red line is for this particular variable sources, how it changes, so the number of days in unit, how it changes across time. And in comparison, another source in the same observational block using the same flux calibrator. So the other sources looks pretty stable. While this source, it really changed by a factor of 10 over the time of a few hours. Yeah, and those observations later, you can see it seems to be faint, getting fainter. But yeah, and then when you interestingly, this is the continual flux. When you look at the CO flux, this is average CO flux over the red phase, the outburst phase, and the blue phase, and the last one. So the CO flux looks pretty similar, not much change. It's really the continual flux changed by order of magnitude.
So what's your interpretation?
Our hypothesis is this disk has it's actually a binary at the center and maybe very close binaries, and they may have some magnetic field reconnection and during that, yeah, synchrotron radiation.
Do you have polarization information?
No, we don't have. Yeah, maybe I should need to talk with Leslie.
So the flux is only in the center that the change.
Yeah, it's a
a
point
resolved
of-
flux, right?
Yeah, not resolved.
It's really hard to, yeah, okay.
Yeah.
Other questions? Yeah. So the spread in the disk mass is
Uh-huh.
quite striking, you know, a couple orders of magnitude.
Yeah, it is.
And this is within a sample of similar age and similar mass, so there's some other property that must control the disk mass or something like that, I think.
Yeah,
So
it
what's your thinking there?
I think there must be some initial condition spread, so not just the gas mass, right? So when you look at the dust, yeah, you see the similar spread of 2 orders of magnitude there. So even for similar ages and similar stellar mass, you see a big spread on the top.
Have you plotted it versus the mass, luminosity, or to compare, instead of binning it by region, bin it by mass and see if there are any differences? We do see differences in other studies where the mass.
Yeah.
The
We-
mass, stellar mass, sorry.
Yeah, we tried to plot with stellar mass, but we don't see
see
significant
the
correlation. Yeah. We also try to plot with individual ages.
Yeah.
Really, it has some hint of decreasing with ages, but yeah, not significant. Yeah, we tried a bunch of things, stellar luminosity,
Yeah.
effective temperature.
You would, yeah. Yes.
Maybe, two maybe very naive questions. The first one is, how do you distinguish the contribution from the central star or binary to this?
Yeah, so for thermal emission, the photosphere radiation at millimeter wavelengths is negligible compared to the disk itself. If you look at the very old image, which is basically here, right? So what do we measure? The disk contribution is here, the photosphere contribution is many orders of magnitude lower.
So is this a real measurement or just the theoretical?
This is a real measurement, but the photosphere projection is based on the effective temperature of the star, right? So black body radiation at millimeter wavelengths.
But you also mentioned that strong flare maybe from central star or binary. So
That's a different mechanism. That's like we think it's synchrotron radiation, not the thermal radiation.
so will your measurement include synchrotron? emission?
No, we think most of the source to be thermal emission dominated. It's just that one showing the flare, which is pretty rare. Yeah.
The second question is that, do you take into account like inclination angle in your analysis, or do you normalize the disk size, you know? like,
Yeah,
in your
so
analysis?
we know the inclination angle of those sources because you can measure the major axis versus the minor axis. So that gives you the inclination angle of the disk. So when we estimate the gas mass, we're considering the inclination angle for those measurements. So for the models, we have three inclination angles, 0, 30, and 80 degrees. So we're trying to match the ones which closest to the observable.
Charles, again?
I had a general question about the status of the turbulence and disk constraints from observations. So you listed the clarity at all.
Yeah.
At the beginning as, no detection, but I thought that there were plain detections.
There is one detection DM tau, they detected turbulence, but the other ones are mostly upper limits. Yeah, they constrain the alpha parameter to less than 10 to minus 3 in general, but that's not the direct constraint on the different location of the turbulence, and it's a very small sample so far, has been like 5 or 6 disks.
Any other questions? So, this is a question.
May I?
Oh, yes. I didn't see you. Yes, go ahead.
Thank you. Early on, you showed a slide with a cartoon showing the different phases of evolution from a cloud to a disk, etc. Could you put it back on, please?
Is this the one you're talking